Okay, let's dive in. There's a lot of excitement about the latest wave of AI models, right? The ones that seem to show their work, generating step-by-step reasoning like chain of thought,
Yeah, exactly. They're calling them large reasoning models, or LRMs.
LRMs,
Yeah.
and they feel like they're getting closer to genuine thinking.
They really do. We're talking about models like OpenAI's O1 or O3, DeepSeek R1, Claude 3.7, Sonnet thinking, Gemini thinking. What makes them different is this ability to generate, detailed internal processes, sequences of steps, reflection, that sort of thing, before giving a final answer.
And they seem to work pretty well, right, on standard tests.
Yeah, on many standard reasoning tasks, this approach has led to better performance, and that sparked hope that maybe they're a step towards more general AI.
But here's the burning question, the one that keeps researchers up at night. What are these models truly doing? Is it real flexible reasoning, the kind that can handle anything you throw at it?
Or is it something else? Something maybe more fragile.
Exactly. And that's really what our deep dive is about today. We're cracking open this paper from Apple researchers with a title that really grabs you, The Illusion of Thinking.
Yeah, that title isn't just catchy, it gets right to their core investigation. The paper meticulously looks at how these LRMs perform, not just generally, but specifically as problems get harder and harder.
So they're going beyond just checking the final answer.
Right, they're trying to probe the fundamental capabilities, how they scale, and most critically, their limitations.
So for you, our listener, our mission today is to kind of cut through the hype. We want to get a clear picture of what these powerful reasoning models can fundamentally do, and maybe more importantly, where their abilities just hit a wall, especially as complexity ramps up.
Yeah, we're going to use this paper's insights to peek behind the curtain of their supposed thinking process.
And why is a study like this even needed? Don't we have benchmarks already?
Well, that's the problem. The paper points out a couple of big issues with typical AI benchmarks, things like standard math or coding problems. First, there's the problem of data contamination.
Ah, meaning the models might have seen the answers or something very similar during training.
Exactly. They could just be retrieving memorized patterns rather than genuinely reasoning. And second, and this is maybe more limiting for understanding how they work, most benchmarks only score the final answer,
Right, you don't see the steps, the process.
which is crucial if you want to understand their reasoning capabilities, not just their test-taking skills.
So these researchers needed a totally different environment, something clean, controllable,
Precisely, and that led them to use controlled puzzle environments.
puzzles, like
Yeah,
Tower of Hanoi, things like that.
exactly like that. Puzzles are really ideal for this kind of analysis. Think about Tower of Hanoi. You can make the problem harder just by adding more disks,
Right, the core logic stays the same, but it just gets bigger.
predictably bigger. And that control lets researchers avoid data contamination entirely. These specific puzzle instances, especially complex ones, aren't just sitting out there on the internet for the models to have seen.
Okay.
And because the rules are simple and explicit, it forces the model to rely on algorithmic reasoning based only on the rules given, not general knowledge or, memorized solutions.
And the real power you mentioned is seeing the process.
Yes. They can use a simulator to check not just the final result, but every single move, every intermediate step the model proposes. This is how they get their window into what's happening inside the model's process.
Okay, so what kinds of puzzles did they actually use?
The paper focuses on four classic types, good examples of different kinds of structured problems. There's Tower of Hanoi, moving disks between pegs, add disks, and the optimal moves grow exponentially. Think 2 to the n minus 1.
Exponential. Okay, so adding just one disk basically doubles the difficulty.
Roughly doubles it, yeah. Then they use checker jumping, swapping checkers on a line by sliding or jumping. This one has quadratic complexity n squared, roughly, so difficulty grows with the square of the number of checkers.
Still gets harder fast, but not quite exponential.
Right. Then the classic river crossing puzzles, like missionaries and cannibals getting people or things across a river with boat limits and safety rules. Complexity there depends on the number of pairs crossing.
Okay.
And finally, blocks world. Just rearranging blocks and stacks. Again, complexity increases with the number of blocks.
So by adjusting this n, the number of disks, checkers, whatever, they can precisely fine-tune how hard the problem is and just watch how the models react.
Exactly what they did. They compared several thinking models like that Claude 3.7 Sonnet Thinking and DeepSeek R1 against their standard non-thinking counterparts.
Like the base Claude 3.7 Sonnet or DeepSeek V3.
Right. And they also looked at things like PASEK, which is basically giving the model multiple tries, comparing performance with an equivalent amount of computation.
Okay, and what did they find when they plotted performance against this controlled complexity?
They discovered something really striking, something quite different from what you see on, say, math benchmarks. There weren't just small differences. There were three very distinct performance zones, or regimes, based purely on how hard the puzzle was.
3 regimes. Okay, this sounds crucial. Walk us through them.
All right. The first zone is low complexity. And here's something surprising. For the simplest versions of these puzzles, the standard non-thinking models often perform just as well as the thinking models.
Wait, really?
Yeah, or sometimes even slightly better. And what's more, the standard models were more token efficient. They used fewer resources, fewer tokens to get the answer.
Huh. So the thinking part wasn't always helping.
It suggests that generating these elaborate thoughts for easy problems isn't necessarily beneficial. It can be wasteful, maybe even slightly detrimental sometimes.
Wow, okay. That's the first hint of maybe this illusion idea. Thinking isn't always better.
Right. But then you move into the medium complexity zone. And this is the sweet spot where the thinking models really start to show their advantage.
Okay.
Their ability to generate longer, more detailed internal steps seems to help them navigate the trickier logic compared to their non-thinking siblings. You see a noticeable performance gap emerge here. The thinking helps.
Right, so thinking does pay off when the problem actually requires more substantial effort. Makes sense.
Yeah.
What about the highest level, when things get really tough?
This brings us to the third and arguably most critical zone, high complexity. In this regime, things take a really sharp turn. Both the thinking and the non-thinking models experience a complete performance collapse.
Not just worse performance, but collapse.
A collapse. Their accuracy plunges to zero. Now, the thinking models might hold on a little longer. They might push that boundary slightly further before they collapse.
Okay.
But ultimately, they hit the same fundamental limit. They just stop being able to solve the problems.
At all. A complete collapse to zero accuracy on harder problems. That feels pretty significant.
It is, and the paper really zooms in on this collapse. You see it across all the thinking models. They tested O3 Mini, DeepSeek R1, Claude 3.7 Sonnet Thinking. As complexity increases, accuracy just drops off a cliff beyond a certain point, which varies a bit model by model.
And there was that truly astonishing finding related to this collapse, something about how much they think as problems get harder, right?
Yes, this is perhaps the most counterintuitive result in the whole paper, and it really underscores that title, The Illusion of Thinking.
What is it?
As problems get more complex, as they approach that point where the models collapse, these reasoning models paradoxically decrease their reasoning effort.
Hold on. When the task gets harder, they think less.
Exactly. You'd expect, right, that faced with a tougher problem, a reasoning process would scale up, generate longer, more complex chains of thought to try and tackle it.
Yeah, absolutely. More effort for harder problems.
But they do the opposite. They seem to reduce their internal exploration, use fewer thinking tokens. And the paper confirms this isn't because they're hitting some token limit in the API call. They had plenty of budget left.
So they could think more, but they choose not to, right when things get difficult.
Precisely. This behavior strongly suggests a fundamental limit in how their internal process scales with the problem's inherent difficulty. They don't rise to the challenge, they seem to shrink from it.
Wow. That's a powerful illustration of the illusion. It suggests they aren't genuinely, wrestling with the problem's difficulty in a flexible way. Maybe they're hitting some hard boundary in their architecture or training that just makes them falter and give up when pattern recognition fails.
That's certainly a strong interpretation supported by this data.
But the puzzle setup allowed the researchers to look even deeper, didn't it? Like inside the actual steps generated during the thinking process.
Yes, exactly. They could analyze the intermediate steps, the potential solutions the models came up with within their internal thinking trace. This goes way beyond just checking the final answer. It looks at the path taken.
Okay, and what did that inner look reveal? Did the quality or the pattern of thinking change with complexity?
Oh, absolutely. It showed distinct and often pretty inefficient patterns depending on the problem's difficulty level.
Like what?
Okay, so in the low complexity zone where we saw the standard models sometimes did better, the thinking models often found the correct solution relatively early in their trace. But then
They'd keep going. They'd continue exploring incorrect paths after already finding the right answer internally. The correct solutions appeared earlier in the sequence of thoughts than the incorrect ones.
So they solve it, but then keep rambling and making mistakes. That sounds like Overthinking.
That's exactly what some call it, overthinking,
Mm.
generating unnecessary, often wrong steps. Even after solving it correctly, it's just compute inefficient.
Okay, not very smart for easy problems. What about the medium zone? Right, in the medium complexity zone where the thinking models actually had the pattern reversed,
Yeah.
the models would first explore incorrect solutions, often quite extensively.
So they struggle first.
Yeah, they go down long paths initially. The correct path or solution only emerged much later in their thinking process, after a significant amount of exploration, trial, and error within the trace.
Okay, so at medium difficulty, they kind of thrash around internally, but eventually find the right path through that extended thinking.
That seems to be what's happening. But then we return to the high complexity zone, the collapse point.
And what did the traces look like there?
Looking inside the thoughts here reveals the stark reality. In this regime, the models failed to generate any correct solutions within their thinking traces. Zero. The accuracy of the steps within the trace itself remained near zero.
Wow. So the trace analysis confirms it. The collapse isn't just about fumbling the final answer. It's because their internal thought process itself completely breaks down. They aren't even exploring valid paths internally anymore at high complexity.
That's right. It really highlights these limitations in their ability to self-correct or maintain a coherent logical search as things get genuinely difficult for them.
Okay, that paints a pretty clear picture of the limitations based on complexity. Did the paper find any other weird behaviors?
It did. Beyond these complexity-dependent regimes and the collapse, the paper also points out some other behaviors that are, frankly, uh, pretty puzzling.
Leveling how? Give me an example.
Okay, one really surprising finding was about their ability to perform exact computation. So the researchers took the Tower of Hanoi puzzle again, but this time, instead of asking the model to figure out the solution,
Yeah.
they gave it the explicit algorithm, the step-by-step instructions directly in the prompt. The model just had to execute the steps.
So basically just follow a recipe. That sounds much simpler than writing the recipe itself.
You'd think so, wouldn't you? But performance didn't really improve much, if at all. The models still collapsed at roughly the same complexity level. They failed to execute the provided algorithm correctly for the harder versions of the puzzle.
That is puzzling. Why would following steps be just as hard as figuring them out?
It's really counterintuitive. It suggests limitations not just in, problem-solving strategy, but in consistently executing long sequences of logical operations and maybe verifying those steps internally, even when told exactly what to do.
So they struggle to reliably follow instructions, especially as those instructions get longer or the state they need to track gets more complex. That's a pretty significant limitation for anything requiring precise procedural execution, isn't it?
It absolutely is. And there was another puzzling thing they saw.
What else?
They observed really inconsistent reasoning capabilities across different puzzle types. Even when the complexity, may be measured by the number of moves needed for an optimal solution, was similar or even lower for the puzzle where they failed badly.
Okay, give me the example there.
For instance, they found Claude 3.7 Sonnet Thinking could handle Tower of Hanoi problems requiring, over 100 correct moves for N10 before making a mistake. Pretty good. But then, in the river crossing puzzle, on a version, N3, that required only 11 total moves for the optimal solution, far, far fewer than the 100-plus moves it handled in Tower of Hanoi, it failed after only about 4 moves.
Wait, it can do 100-plus steps fine in one puzzle, but fails after 4 steps in another, easier puzzle. That inconsistency is weird.
It is weird. If it has the capacity for that length of correct sequential action in one context, why does it fail so quickly in another, seemingly simpler context?
Any ideas why?
Well, the paper speculates this might relate back to the training data again. Maybe complex river crossing puzzles like N3 or higher just aren't as common or well represented online or in training sets compared to something super classic and ubiquitous like Tower of Hanoi.
Ah, so it might have learned or memorized strategies for Hanoi better.
Possibly. It suggests the models might be relying more on memorized patterns or strategies picked up from the data distribution, rather than possessing a truly generalizable reasoning ability that applies equally well across different problem structures, even if the underlying logical demands seem similar.
Which, again, brings us right back to that central tension, doesn't it?
Yeah.
True, flexible reasoning versus really sophisticated pattern matching and interpolation based on what they've seen before.
Precisely. These inconsistencies really highlight the open questions about the fundamental nature of reasoning in these systems.
Okay, let's try and pull this all together then.
Yeah.
What are the core takeaways for our listeners from this deep dive into the illusion of thinking?
I think the paper provides some really compelling evidence that current large reasoning models, despite these advanced thinking mechanisms they have, hit fundamental limitations, particularly in these controlled puzzle environments.
And the key finding is these three distinct performance regimes based on complexity.
Yes. They can struggle or be inefficient on easy problems. They show a clear advantage in a medium sweet spot, but crucially, they experience a complete performance collapse on high complexity tasks, both thinking and non-thinking models.
And that collapse comes with that really weird paradoxical behavior of decreasing their reasoning effort, using fewer thinking tokens just when the problem gets hardest.
Exactly, which strongly suggests a fundamental limit in their ability to computationally scale their internal process to match the actual difficulty of the problem. And the analysis of their internal thinking traces backs this up.
Right, showing that inefficient overthinking on simple problems and then a complete failure to even explore valid paths internally on the complex ones.
Yeah, highlighting limits in self-correction and maintaining logical coherence.
And then there were those puzzling findings that even giving them the exact algorithm doesn't prevent the collapse, and that their performance varies so dramatically and inconsistently across different types of puzzles.
Right. All of which really challenges the idea that they possess robust, generalizable reasoning skills applicable to any problem structure. It raises crucial questions about the nature of the capabilities we're observing.
Making that title, The Illusion of Thinking, feel pretty apt, at least when considering these complex, novel problems where their apparent reasoning just breaks down or behaves paradoxically.
It does feel fitting in that context. Now, it's worth noting, as the authors do, the limitations here. These are controlled puzzle environments, a specific slice of reasoning. Most access was via black box APIs.
Right, they couldn't see everything inside.
And assuming perfect validation of every step in the puzzles might differ from the messier reality of real-world tasks.
Sure, caveats apply.
True, but even with those limitations, the core findings about the complexity-dependent regimes, the collapse, the counterintuitive token use at high difficulty, they seem pretty profound for understanding the boundaries of what current LRMs can actually do.
Absolutely. It definitely changes how you might think about evaluating these models and, maybe more importantly, how much you can rely on them for really complex, unfamiliar tasks. So to leave you, our listener, with something to ponder after this deep dive. If these advanced AI models, the ones specifically designed for reasoning, struggle like this, if they struggle to consistently follow logical steps or generalized strategies, even on these relatively simple controlled puzzles once they get complex enough, what does that really tell us about their current ability to navigate and solve truly novel or highly complex problems out in the unstructured, unpredictable real world?
It's definitely a question worth serious consideration.
Thank you for joining us on The Deep Dive. We hope this look inside the illusion of thinking gives you a clearer, maybe more nuanced perspective on where we stand with large reasoning models today.